Welcome back to the series of lectures on high-performance scientific computing. In the last class, we just had started talking about message passing interface or MPI programming for distributed memory machines. We had seen a simple hello world code. We had seen how MPI is initialized and sent across as different processes to different processors, some of them which could be on the same machine and some on different machines. We had seen how to get a unique process ID for each of these machines and also on how to finalize and close these MPI programs. We had implemented this on a simple MPI hello world and then we had tested it out. We also saw that there was no particular order in which these codes are executed, in the sense that there is no preference to these process IDs. So now let us decide on how to do a certain bit of control for this code. The first question we need to ask is, do all nodes really run the same code? Is it useful if all the nodes run the same code? Obviously not. We would like the same code to run on different data sets or have different branches. These codes do run independently, but you cannot do much unique work unless you know what their process ID is. And you can use this process ID to change their behavior. You can also have extreme control and ask different process IDs to execute different bits of code. For example, if I put an if condition like, if my process ID is 0, please call the routine Space Invaders. If my process ID is 1, please call the routine crack passwords. If my process ID is 2, please call the routine weather forecast. Obviously, routine Space Invaders, which is a game, routine crack passwords is a malicious program, and weather forecast, which is a useful program, are all going to be run distinctly on process ID 0, 1 and 2 respectively. So we can essentially trick the parallel program into running different codes or different programs by itself using these sort of if constructs. And we can have the MPI codes run completely unrelated programs as well by putting them into one executable. But usually this is not very useful. Ideally, what we would like to do is to have a very similar code or the same code, but working on parts of different data, or when you sort of decompose the problem, split up the problem into several parts. So let us see how we can do that. The other notion that we had was the fact that all these MPI processes, while they are unique, they do not have any preference, i.e. there is no central authority, there is no captain of the team. So there is no concept of a master and slave. But usually when we write our parallel algorithm, we need some sort of coordination. We need some sort of single process which will do some sort of gather. For example, let us go back to the idea of the bag of integers which we needed to sum. Now, if I had 10,000 integers which I needed to sum, and let's say I split it parallelly amongst 10 processes, each process then would compute its local sum. But then one process had to compute the global sum from these 10 local sums. So which process should do that? So we need to make some sort of decision at this point of time. So we can now say, if my process ID is 0, then I can go and do the global sum or have some sort of master code routine. Else I will run only the slave routines, which means I will only compute my local sums. Obviously, in the case of Hello World, everybody ran this routine. The only difference in that output is the process number. Whereas if I say that, okay, no, if my process number is 0, then I will go and do the global sum. Now, why do we choose 0 preferentially as the one as a master? There is no particular reason why 0 should be the master apart from convenience. Because no matter what the size of the program or no matter what is the amount of resources we require to run a particular parallel program, there will always be a 0 process ID. If we take 2 processes, it will be 0 and 1. If we take 4, it will be 0, 1, 2, 3. So as you can see, there always exists a 0 process number, and hence it is usually convenient to denote 0 to be the master process. The next thing is what we need to look at, the MPI communication rank, which gives the communication of what my process ID is. We have discussed this in detail in the Hello World program. All of this will be useless if we are unable to send and receive messages. The Hello World program is just a small illustration, but we have really not shared any data amongst the distributed memory machines apart from the simple screen output. Now let us write a simple program where it will run on 2 processes and we will send a simple message, the number 42, from process 1 to process 0. And then process 0 will print it out. So this will be the first pair of communications that we will be doing on a simple code. So we need a function to send the message. And this function has to be a message passing interface function, because this could go locally to the same machine, it could go via the interconnect to a remote machine as well. So if you want to send a message, you need to call a routine like MPI send or a function like MPI send. What are the arguments that this function needs to be provided with? You obviously need to provide a pointer or the location of the memory for the data that needs to be sent. In this case, whatever number that is to be sent. The second thing that we need to figure out is how many such items need to be sent. Now, obviously, it will become cumbersome if we are sending data one item at a time. So ideally, we would like to send large chunks of data together in one shot. Very simple to stuff when we are trying to post or courier things. So the next argument is how many number of items we want to send. Is it a single data variable or is it an array of multiple data variables? So that's the second bit, is the number of items to be sent. The third item or the third argument is what is this data type? Because we know that different kinds of variables have different memory lengths. For example, an integer, or if it is a floating point number, or if it is a double, or if it is a short number, or if it's a character. So there are lots and lots of data types that are supported by MPI, the list of which is given in this slide. So essentially the first 3 arguments tell you the location, the actual memory location of where the data that we need to send resides, or the start point of that data. It tells you how many similar data items are there, and it tells you the data type, which in turn tells you the length of that data. For example, in this case, we are saying it's an MPI integer. Let's say the integer on this particular system is given by 4 bytes. It could be 4 bytes, it could be 8 bytes, it depends on the machine's definition. What we are essentially telling the MPI send function is that please go to this memory address and take one integer from there, which is essentially take the next 4 contiguous bytes and transmit it. The fourth argument is the destination of this message. Where do you want to send it? And in this case, we are going to send it to process 0. So whenever we are sending a message, we need to decide where we are sending these messages. And in this case, for this simple program, since we have decided we are going to send the message from process 1 to process 0, our destination is going to be process 0. When we are sending messages, we could be sending multiple messages to the same process. So it is always a good idea to sort of tag each of these messages uniquely. So when the messages come in, you realize which tag is there in this message and you put the message in the appropriate memory location. So this is useful when we are sending multiple bits of data to one process and we need it to send it to specific memory locations on that particular process. Here we have just put 10 as a random tag because in this case we are just using one data member which we need to send. So the other thing, the last argument is something called as the MPI communication world. Essentially what we are trying to say is that this machine where we are trying to send this message or this process where we are trying to send this message exists in this MPI communication world. In this simple problem, we do not really care about subsets of different processes. All the processes are equal and are part of the same set. So this is the default setting for sending messages to all these processes. In advanced MPI, you can create subsets of MPI processes where I will send the message only to a subset, not to the entire communication world. But for now, we will leave it at the default of communication world. If there is a send, there has to be a corresponding receive. And receiving a message is very simple and has a symmetric sort of nature. So the function MPI receive will first give you the address or the memory location where the received number needs to be written or stored. The second thing it gives is how many items do I need to receive. So the first item tells you the memory location where I need to start writing the data, and the total number of items that need to be written is the second argument. Again, we need to know what the data type is because we need to know how many bytes to write correctly from the starting of that particular memory location. And MPI int is the data type. And in this case, since we are sending an integer, we should be receiving an integer. The next two arguments are something which is very interesting. Now, we can receive a message from a particular source, or we could denote it saying that I don't care, I can take the message from any source and put it at that particular memory location. Now, this depends on the construction of your algorithm. And when we look at some advanced programs, we will see how this is useful. But for a simple program like this, I can say, I don't care where do I receive the message from, as long as it's coming from some source which is there in my communication world, I'm ready to take it. So I'll say, I'll take the message from any source, and that's done by the tag MPI any source. Very similarly, I can say that I don't care what is the tag of the message. If I had said, no, I want to take data of a specific tag only to place it at that specific memory location, then I would have a specific integer. So I would know how to sort of sort my data that is coming in from any source. Or I could just say, I don't care, I can take data with any tag and put it into this address at number to receive. We already discussed what MPI communication world is. The MPI receive function has one additional parameter, which is the status function. So it basically tells you the status of the data, which includes the source and the tag of this message. So let us now look at a simple send and receive code written in C. So here we say that we have my process number, I have then two additional integers, one is number to receive, which has not been assigned any value, number to send which has been initialized to the number 42. That is the message we would like to send. We have the MPI status variable which will give me the data structure of the send and receive, which needs to be initialized. And then after that, we have MPI init, which initializes the MPI environment. The MPI communication rank tells me my process ID, my unique process ID from the communication world and puts it into the variable myPenum. And here is where the program starts to diverge. If I say my PEnum is 0, then I am going to go and do a receive function. So I am ready to receive if my process number is 0. And I will receive it into this particular memory location, number to receive, and I am going to receive an integer of one particular size or one integer. I don't care from where I receive it. It could be from any source. It could be from with any tag. And then once I receive the number, I am going to print, I have received this number, and print it out and get out of this if loop. If my process is not 0, process ID is not 0, I am going to do a send. And I am going to send this particular number to 0, that is a destination. Remember, I am not sending it to everybody, I am just sending it very particularly to process 0, and I am sending one integer in the communication world. And finally, if this send is done, then we move on. So the program flow will be such that MPI is initialized. There are several copies of this program which are initialized. Each copy of that program will get a certain specific process ID. If the process ID turns out to be 0, it will go and start the MPI receive function. If the process ID is anything other than 0, it will go and do an MPI send function. And once the send is done, it will go ahead, and correspondingly, if the receive is done, it will go and print this and then get out of this if structure. Finally, then there will be an MPI finalize, which closes the code. If I were to look at the same code in Fortran, it is very, very similar. I have the same variables and we have one extra variable, the error code. So I call the MPI init function, I then call the MPI communication rank function, I set number to send to be 42, I put the if condition saying that if my process number is 0, please do MPI receive and then print number, and if my process is 1 or anything else, please go ahead and do the send and finalize the code. So this is the Fortran version of the code. Let us now go and execute this code. We will now just verify this code in C. So we have the same exact code which is written in C. Remember, we will now compile it using the MPI cc command, and we will compile this code and we will put it in the output send receive. To execute this code, we say MPI run minus NP. In this case, I will use two processes, send receive, and see what happens. And we say the number received is 42. Let me now increase the number of MPI processes, say from 2 to 8, and see what is the output of this program. We will still get only one printout of 42. So what is essentially happening over here is that process 0 is waiting for a response or waiting for the receipt of one particular integer. The 7 other processes, 1 through 7, are sending data to process 0. But the moment one process, we don't know which one, receives this data, we then finish up with the communication and we are done. So only one output is received. To verify this, we can modify this code slightly. So we can go here and instead of saying number to send, we can slightly modify the code over here by saying that number to send is equal to my PE num, and we will remove this 42 from here. We will just declare number to send over here, but the assignment of number to send will be given by what is PE num. Okay? Now, if this code is run, let's see how it behaves. First, we will compile this code, and then we will run it with 8. In this code, process 2 came out first and sent the message to the 0th process. If I run it again, oh, it's 2 again in this case. So it looks like in this system, there we go, where we have a slightly different number coming, which is 4. Now we have 4. Now we are back to 2. So this behavior is random. So in this case, we are seeing that the process 2 is getting finished first most of the time. Some of the time, process 4 is getting finished. So this is totally random based on how the operating system is scheduling these codes. And so now let's go back to our discussion. Thank you. In the next class, we will see some advanced implementations of this code.